In this video, we're going to tackle the final task of the exercise, task 20. And in task 20, we're going to do a price reduction analysis for treatment B. So this is something which some HTA agencies conduct in practice, such as CADTH in Canada. They will do a probabilistic analysis at different possible price reductions for the treatment in question and identify what happens to the ISA. Right, so it might be, as in our case, the ISA is too high to be cost effective at the list price. Well, how much of a price reduction would be required for this treatment to appear cost effective? And there are a couple of ways this can be done. One is in just fixed decrements in that price, so a 10% reduction in the price, 20%, and so on, all the way down to 90%. And another way of doing it would be to calculate the exact price reduction required in order for the ISA, for the new treatment, the expensive treatment, to be exactly equal to that cost effectiveness threshold. And we're going to do both of those in this final task. We're going to go back to our probabilistic results sheet, which is on the right. And when we come down to the bottom, you'll see that there's a new table at the bottom, the final table that we're going to deal with here. And this is where we're going to do our probabilistic price reduction analysis. So again, we have this current value, these set of current value cells. And what we're going to do in these is we are going to, very much like in the previous task, we're going to get some values in here which then get, copied down. So we need the expected incremental cost given all of the current settings in the model, in particular the price reduction for treatment B. So the expected incremental cost, we can just pull that from our table at the top. It's this one here. The expected incremental quality. And again, you could pull these in from the discounting sheet as well if you wished. Entirely up to you where you get these from. The expected incremental net monetary benefit. That's this one here. And then finally the ISA, which is only calculated on this sheet. So you'll have to pull that in from here. Okay, so these are the live values, if you like. As we play around with different settings, these will update, and we're going to copy them into this table below. So step 20.2 is to complete the 0% price reduction row. And as it says here on the left, as it stands, your model incorporates no price reduction. So on the left, I'm just going to go to the input sheet. And if we go across way back in the very first task, when we put in the treatment costs, for treatment B, we had a list price of 3,000, we had a price reduction of 0, and that gave us a final price of 3,000. And it's this cell, this price reduction, that's the really important cell for this particular task. So right now it's set to 0, so there is no price reduction. And so what we have here on the right, this is the expected incremental cost, expected incremental quality, expected incremental net monetary benefit, the ISA, where there is no price reduction. So we're going to copy these, and we're going to paste them here where we have a 0% price reduction. And we're going to do paste special values. We just want the values. Okay, so that's step 20.2 complete. Now we need to change the price reduction to 10%. So return to the input sheet and, update that to 10%. And you'll see that the price of treatment B has now fallen to 2,700. And tick the box when you've finished that. Okay, now step 20.4, import the 10% price reduction row to the data table. So we have a small challenge here, which is that unlike when we update things on the settings sheet, so the time horizon, the threshold, discount rate, those things are applied after the Monte Carlo simulation has been performed. So it just results in, we have to wait a few seconds for the sheet to recalculate, but otherwise it's no big deal. When you update things on the input sheet, unfortunately, that requires you to redo the Monte Carlo simulation. And so updating the price of treatment B means we now need to repeat our probabilistic analysis. And if you recall back on the simulation sheet, if I go back to the simulation sheet, you would have different values that we are copying down on that simulation sheet. And so typically you'd write a short macro to do this, right? You'd have a macro in Excel that would update the price reduction, and then it would repeat the Monte Carlo simulation. But we're not writing macros for the purpose of this exercise. So what we're going to do here is we're just going to tick this box, and the correct values that you would get are going to be, automatically imported onto our probabilistic results sheet. So in those gray cells that you have there next to the 10%, you can see these values have just been automatically imported. Saves us having to run the Monte Carlo simulation again. Okay, so what do we do now? We can calculate the step change in the expected incremental costs. So something to bear in mind is that these two values, the expected incremental qualities, are exactly the same. It looks like there's a tiny little bit of rounding error in the 15th decimal place that is very likely coming from floating point error. But these are effectively the same, right? At least to a reasonable number of decimal places. And the reason being that changing the price of treatment B has no impact whatsoever on the qualities for either treatment. It has no impact on the incremental qualities. Now, it does impact the incremental costs, of course. So those have fallen from 46,000 down to about 36,000. So what we can do is we can calculate the step change in these incremental costs. And we're going to do that in this cell just here. So by how much have the incremental costs fallen due to a 10% reduction in the price? And we can use that to estimate, or to calculate, I should say, we can precisely calculate what the incremental costs would be if we were to have a price reduction of 20%, 30%, and 40%. Now, we need to be clear before we continue. This works for a cost parameter where that cost parameter has no nonlinear relationship with any other parameters in the model. So that includes the cost of treatment B. This sort of approach would not work if you were doing a sensitivity analysis or a scenario analysis on, let's say, one of the probability parameters. Okay, one of those parameters where there are nonlinear relationships between that parameter and other parameters in the model. It works here because when you change the price of treatment B, so let's be clear, that will have an impact on the incremental cost, and the impact is not actually trivial to work out. So if you were to reduce the cost of, well, you can see what we did here. We reduced the cost by $300. It went from $3,000 down to $2,700. So there is a $300 reduction in the price of treatment B. Well, has that resulted in a $300 reduction in the incremental cost, the expected incremental cost? Well, no, because treatment B is not only provided once. You have treatment B every cycle. And it becomes a bit complicated to figure out the reduction because patients are living for multiple years. Patients are dying at some point. We have discounting being applied. So even if there is a $300 reduction in future years, we're not valuing it as a $300 reduction. Okay, so it actually becomes really quite complicated to convert that $300 reduction in the price of B into the impact on the incremental cost overall over the lifetime horizon, or I shouldn't say lifetime in this model, it's a 5-year time horizon. Given discounting, it's pretty complicated. But that's what our model's for. That's what the model does. And when we ran that additional simulation at 10%, when that was done for you, the model took all of that into account. Once you've identified that relationship between an X%, in this case 10% reduction in the price of B and the change in the incremental cost, that relationship applies to the next 10% reduction. If there's a $9,000 roughly change here, well, then there'll be roughly a $9,000 change for the next increment, the next reduction in the price, and so on. So that's what we're going to do now. So in this cell here, in I151, we're going to calculate the reduction in the price. And it just says here, this should be negative. So when I say we're calculating the reduction, we're actually calculating the increase, which is negative. Okay, so it's going to be this minus this. Okay, so negative 9,282. That is what happened to the expected incremental costs when we changed the price. Okay, so that's correct. Now the next step is to extrapolate this for the other scenarios. There's no need to run the Monte Carlo simulation over and over again when we can just do the extrapolation. So what would we put in this cell here? how do we extrapolate this? What formula can we use? So what we could say is this cell just equals the cell above plus this cell, right? Which is going to effectively subtract 9,282. Now, as this gets copied down, well, I will copy it down in a moment. It's not going to do it automatically. But as I copy this down, I just want to make sure that that row 151 stays fixed. So I'm going to put a dollar symbol in. Okay, so it's happy with that. And then I'm going to select that cell, just wait for the formatting to be applied. I'm going to copy that down here. There we go. So you can see that when you get a really substantial price reduction, actually this is now, you're now saving money with treatment B. Okay, I'm not entirely sure why the formatting didn't apply to that cell, just a small little bug there, but we will continue. So we're now looking at the expected qualities. Well, that's easy to extrapolate because it doesn't change. So we'll just do equals, and we'll say pick the top one, and then just, I'll wait for that to be marked. One thing to bear in mind about this, you can see it ends with a 3 and this ends with a 2. Computers, when they do floating point calculations, they can get these errors in the very last decimal point. That is actually quite common. And so what the automated marking system does here is it just looks at 6 decimal places, make sure that it's accurate to 6. It does not matter that the very last decimal place is incorrect. Okay, so all of these are effectively identical because the change in the price of treatment B has no impact on the qualities. So that's 20.7 complete, 20.8 has been unlocked. Now, what do we do here? We need to calculate the expected incremental net monetary benefit for the other scenarios. And we can do that because we know that the expected incremental net monetary benefit for this particular price reduction is going to equal whatever the incremental qualities are, multiplied by the threshold, S threshold, and then we subtract whatever the costs are. Okay, and then we can just copy that, paste it here. And then finally, in a moment, it's going to unlock the next step, and we need to calculate the ICEs in this table. And so 20.9, we're doing the ICEs, and we know the incremental cost, we know the incremental quali. So it's just going to be this divided by this. And you can see there's a pattern, right? There's the expected incremental net monetary benefit was negative, but once you get to a price reduction somewhere between 20% and 30%, the incremental net monetary benefit, the expected incremental net monetary benefit becomes positive. So we're looking at a price reduction somewhere between 20% and 30%. So I'm just going to copy this on and paste it here. And it's not a coincidence that between 20 and 30%, that ISA falls from above 50,000 to below 50,000. So not a coincidence. We're looking at a price reduction somewhere in that range. So that's 20.9 complete. 20.10 has been unlocked. Specify a target ISA for the price reduction analysis. And so what we're going to do is set that equal to the threshold. So we're now going to go down to this table at the very bottom, and what we're going to do now is we're going to calculate the precise price reduction needed for the ISA to equal whatever we put in this box. So we're going to put S threshold. That is the target. So when our willingness to pay is 50,000, we want to know what price reduction is needed to get the ISA to exactly 50,000. That's going to be the minimum price reduction at which treatment B is cost effective. So having done that, we then need to fill in the expected incremental qualities, and that's going to be exactly the same as any of these cells. We can set it equal to any of these. I'm going to do that one, but you can choose any of these cells here. We just need to copy that down. Okay. What's the next step? So in 20.12, back calculate the expected incremental costs. Okay, so we need to do a little bit of thinking here. What are the expected incremental costs that would result in an ISA of 50,000 when you divide these expected incremental costs by these expected incremental qualities? So this cell divided by this cell equals this cell. Okay, so you can rearrange that and say, well, this cell, if you multiply both sides of that equation by the incremental qualities, well, then this cell equals this times this. So that multiplied by that. So 24,000. So if you had an incremental cost, an expected incremental cost of 24,000, then given the expected incremental qualities, which remain constant when you change the price, given that, you would end up with an ISA of exactly 50,000. So this is a really important cell. We've back calculated exactly what we need the expected incremental cost to be in order for the treatment to be just cost effective, right? To have an ISA that equals the threshold. Okay, and then the next one, we're going to confirm that at this particular expected incremental cost and expected incremental quality, the expected incremental net monetary benefit is 0. And we would expect it to be 0 because the ISA is exactly 50,000. But, you know, it's worth checking. So what is this? This equals the incremental qualities. We need to value them at the threshold. And then we need to subtract the incremental costs. Okay, and this brings us on to the very last cell that we need to calculate in our model, this price reduction cell. So the instructions say, enter a formula into G160 to calculate the price reduction required to achieve the target ISA. And so as there's a hint here, your formula should reference the expected incremental cost in D160. So that's this one here. We need to take that into account. We need to look at the step change previously calculated here. And then we need to use one of the costs, the expected incremental costs in 147 to 157. So if we know what these are, and I suppose we also need to know what these are, and we have the step change and we have this, you can figure out what this needs to be. So have a little think about what formula you would put in to get that. Okay, so we know that this occurs, this step change is for every 10% price reduction. So actually we don't even need to select these columns here. We know that this reduction in the incremental cost occurs when there is a 10% reduction in the price. So what we could do here is start off with 10%, so 0.1, whatever that is, multiplied by, and then we can have the D160, so this expected incremental cost, minus D147, so when there's no price reduction whatsoever, okay? And then what should we do? We'll close the bracket and then divide that by the step change. I'm just thinking this through in my head. I think that's going to work. So what are we doing? We're looking at the difference between the expected incremental cost in this particular scenario, where the ISA is 50,000. So 24,000. The difference between that and the incremental cost when the price reduction is 0. So we're getting the difference between the 46,000 we had originally and the 24,000 that we need to get to for this to be cost effective. So there's going to be about a $22,000 difference. We need to reduce the incremental cost by about 22,000. Now we know that for every 9,000, that requires a 10% price reduction. So we're calculating, first of all, that 10%, that $22,000 price reduction that we need. We're then multiplying that by 0.1 to estimate how many increments we need. How many step changes do we need? And then we're going to divide that by the dollars needed here, that 9,000. So let's see if this works. Okay, so 23%. So that is exactly what we would expect, because we said before it was somewhere between 20% and 30%. That is the point where the expected incremental net monetary benefit becomes positive and the ISA falls to below 50. And so it looks, just looking at these, that it's going to be somewhere in between 20 and 30. And so it's no surprise that we get 23%. If we were to have a lower ISA here, well, then you would need a more substantial price reduction. And it's not part of the exercise, but I can probably override this. I can probably put in 30,000. And you can see we need a 34% price reduction. This will be marked as wrong, I expect, because that's not the correct value. But yeah, 34%. And if we had a higher threshold, then I'll put it back to 50,000. Then it's just 23%. If this was 100,000, well, given that the ISA is less than 100,000 when there's no price reduction, that you wouldn't need any price reduction, right? If the ISA, if your target was 100,000, well, actually you could increase the price slightly for the ISA to be $100,000. So there we go. That is the probabilistic price reduction analysis. The very final step says that you can build your model in R. So again, it's more difficult to do this than a simple deterministic model, but much more rewarding. And the advantages of using R in a probabilistic analysis are even greater than the advantages for a deterministic analysis. So when you have a really complicated model in practice, the building this in R will result in a much faster execution time. So it's something to look into if you're interested, how you would build this model in R. But other than that, we can click to say that we are ready to continue. And we get the congratulations message. The exercise is complete. And I would really appreciate if you could provide feedback. So you can enter feedback into this box and I will be able to see that. There's also a link here which takes you to a Google form. If you hover your mouse over where it says, please click here to submit anonymous feedback, please do that. And you can submit feedback and it will make this exercise even better in future. But that's it for the exercise. Thanks for listening. I really hope you enjoyed the exercise and that you learned a lot during the exercise. Thanks very much.